Hello guys, I'm sure you're doing awesome. So in this video, we are going to cover one of the very basic foundational networking concept, which is often ignored by the application engineers or the backend engineers per se. That is HTTP 1, 2, and 3. Often I have found while talking to the developers of a given application, they doesn't even know whether their application's communication stack is on HTTP 1 or 2 or 3. So after this video, you will get a complete end-to-end idea why one protocol or like one version of the HTTP protocol, like 1 or 2 or 3, is preferred over another. And also I will take you through how exactly we moved from the HTTP 1 to HTTP 1.1 to 2 to 3 with case by case basis, and what are the exact pain point which triggered the invention or the policies of the next HTTP version. Okay, so let's get started with this. So for the HTTP 1.0, so what happens, like around mid 1990s, suppose you are a web user, and what generally used to happen is from the user, like using their browser, the user is typing some example.com.index.html, which is quite similar to now also how you are accessing any of the www or the world wide web websites. So at that point of time, what happens is a browser opens a TCP connection to that example.com on a given port, say the port number 80. So this part, if you see, uh, why I have mentioned over here mid 1990 is, although historically we are seeing this basic part has been always same. Like the moment we are hitting a particular website, the browser tries to open a TCP connection to that particular website. Now after that, what happened was, like it sends a single HTTP request to the add connection, and the server receives the request. Once the server, suppose here we are having a given server for this example.com. So once the server receives the request, it sends back the it sends back the response to this level. And once the client receive the response, how it exactly receives the response is in some form of HTML. Like there is a HTML, like your page content will be given there, and this HTML is being loaded into your browser, and that's it. So here, if you see the principle that we are seeing, that is basically one request, okay, and one response, and what the more important thing is one connection. So for every single request, what exactly happening over here is one single connection is being created. Now I hope you already have gone through enough networking concepts where you know what exactly the TCP is, what exactly UDP is, and what happens around their connection. So you probably understand one thing very clearly, that for every single connection there is a considerable resource that are being consumed. So with this basic concepts that every single connection that we create is a resource and time intensive, let's see what exactly the problem of the HTTP 1.0 was. So the first thing that was happening is there was no persistent connection. Now for that, what used to happen is, for each request, a new TCP connection was being created. So each request means a new TCP connection, right? So that meant that the TCP handshake for every request is required, and which led to definitely a lot of resource consumption, and the result was a high latency for the end user. So there was a no scope of the connection reuse, and there is a massive overhead that was going on for the multiple resources like the HTML, CSS, or the images. So that is why the time that used to take just to render a single website used to be a lot. And if I just break it down further, so suppose what used to happen is, like, if you just see how a basic web page is being loaded these days. So alongside the HTML, there will be the other resources as well. So for example, like when this particular response, the request response is going on, this is only for the HTML. So there will be other requests. Okay. So there will be other requests for what? For the JS, the JavaScripts that are being involved, the images that are being involved, and the CSS that are being involved. That is to the very minimal. Like if you see, there are the CDN calls are happening, and there are so many multiple calls are happening that if you just like open any website and go to the developer portal, you will see the reality how many requests are going on. And with HTTP 1.0, what used to happen is, for every single connection, like the full TCP handshake, the SYN ACK that used to happen, and it used to suffer a very high latency problem. Okay, so the impact that was happening, like for the backend engineer, it was a very high increased latency. The SREs, like they could see that there is a lot of connection churns are happening, like more sockets timeout state generally happens during the HTTP 1.0. So to solve this issue, uh, not fully but partially, HTTP 1.1 was introduced, and now we will see what exactly happened in HTTP 1.1 and what are the challenges that we kind of overcame from HTTP 1.0 to HTTP 1.1. So what happened in HTTP 1.1 is, by default, it supported persistent connection. So over here that you see this persistent connection, this is coming by default. So uh, like automatically it is reusing the TCPs, and we are gaining a lot of performance out of it. So this persistent connection uh, that you are seeing for the HTTP 1.1, now here we had different requests, right? For HTML, for the JS, for the images, or for the CSS. But here what used to happen is, there is only one connection that is being created, and very importantly, in sequential manner, or one by one, those requests used to take place. For example, for the HTML, for the JavaScript, for the images, or for the CSS. So if I just go into some further technical details, so not only the persistent connection, it also gave us some very fine-grained control with something called keep alive. So what exactly keep alive is? Now, suppose we want to close a given connection. So here HTTP 1.1 is definitely keeping the connection alive by default. In case we want to close the connection, HTTP 1.1 even gave those provisions. So for example, website is basically downloading for downloading a certain report from a given server, right? So once that server report is being downloaded, there is no point of keeping the connection open. So in that case, we can use this keep alive flag, and we can mark that you can close the connection. So with that, we achieve a very granular control, that with the persistent, it can be a persistent connection, or it can be a temporal connection as well. So as a use case we were talking about, like suppose we want to close the connection after each request. So this is a simple C# code, and here you can see we are sending some headers. So in our headers, we can mark that you close the connection. So what would happen is, every time the download completes, it will simply close the connection, and it is a one-shot response, and server will close the connection immediately once that download request is being served. So how exactly does the anatomy look like for a given HTTP 1.1 connection? So suppose similar way we want to, like as we take in this particular example, similar way uh, we want to make a request. So at first we create a get call. So again, I hope these parts are clear to you, what exactly a get, what exactly a post. So uh, in this REST based mechanism, suppose we are making a get call, and what happens over there is it passes that information around the host, what exactly the user agent, that is basically like it can be any of the browser like the Chrome or Edge, and what it is going to accept like the text, HTML or JSON, and then the connection will be marked as keep alive by default. So what would happen in the response? The response would look like something like this. Let's see how the response comes. So I will just mark this thing as this is the request that goes, and this is our response. So over here, you can see like it gives you the information like from which server it is sending. It can be a Apache version, what exactly is the length of the content, and what is the keep alive. And with keep alive, there are some things like the timeout or the max, which we will also discuss. So what exactly it tells that this is my HTML content, and the server agrees to keep the connection open. And with keep alive timeout 5, it says that keep alive for the 5 seconds or 100 requests. So after 100 requests, definitely a new connection will be opened. Like it cannot be for forever, right? Like for example, from my browser, if I open a connection and like if I just keep it lying there for like hours after hours, then that is definitely I'm using a port, I'm using a connection resources, and which is not at all necessary. So, if we just think through a little deeply, what are the other pain point or the problem we had in HTTP 1.0? There are few other advantages or few other use cases also were solved in HTTP 1.1. So instead of going through them in a dry manner, let's take some real world popular use cases examples, and let's explore how HTTP 1.1 helped us to solve those problems. So streaming logs in the real time has been a real pain point in the HTTP 1.0, because every time you want to create a real time loopback of that particular log, a new connection was to be created. But now with HTTP 1.1, what exactly was happened is, so suppose you are creating something like those GitHub Actions log viewer. Okay, so in that case, what the implementation would look like with HTTP 1.1 is quite simple. So for example, here from the browser, I open my GitHub console. In that GitHub console, I just create a particular GET request of this build logs, and suppose there is a given job ID equal to 567, something like this. Okay, so once we uh, once we make this get call, what would happen is we will definitely we will be getting one this 200 okay response, and from that 200 okay response, there is a particular way we could control it, that is through transfer encoding. So what we can specify over here is how exactly the transfer is going to encode it. And the transfer encoded, if we mark it as chunking, what it will do is it will keep on sending the responses in a chunked manner. Like here, suppose as a chunk one, there is a info that will be passed. So the chunk one info will be something like this. Suppose starting the build, and there are the related informations, and then again the another chunk that will be passed. So suppose similarly it is something like the compiling the code, then there could be the build completed, and in the end there will be like end of the stream will be marked, or the EOS I am writing for the simplicity. So this is the whole This is the whole chunked transfer that is happening over here. And the important point to note is this is being controlled by the server. So server is going to tell the client that we are going to send a transfer, like my response will be a chunked response. So the code at the server end looks something like this. We will just go through it for a couple of minutes so that it gets solidified into our mind. So suppose I call this stream endpoint. Okay, so like build logs job ID, instead of that we can also mark it as something like a stream, just to be in the same page. So what would happen with the stream endpoint is we are going to send a response that my response is going to be a transfer encoded of chunked, and the content type will be a text.plain. And here, although I have written a simple for loop, but generally it is like based on whatever the response it is generating, what it will keep on doing is it will, you can see over here response.body.write async, it will keep on writing the data back, and then at the end it will just do a flush as async. So once this flush async is being done, a one set of data, so only this part of data, the starting build will be flushed, and it will come into the next loop or the next information that it want to pass to the client. Like for our example, it is the compiling the code, it is the build completed, all those information. And in the end, like we do another flush async. So after this flush async, what would happen is it will know that this final chunk, like you can see over here, like we are writing a uh, byte sequence over here with the tab and the new line sequence. This would mean that it is a end of the log, and after that the client would know now I can close the connection. So from here, after that, when the flush async happens, all the data that are being into the stream logs, the streaming side, they will be transferred. So this is a very, very important mechanism, like the chunk transfer that is being introduced in the HTTP 1.1. And even now, like the websites that are using HTTP 1.1, it is like the websites which move to HTTP 1.1, if they are use case limited to this, they are still maintaining this in this particular streaming way. So next very important use case that is being solved by HTTP 1.1 is, suppose you are serving the product images. Okay, like for example that e-commerce like Amazon, or it can be any of your homepage where you know there is a certain product image, that product is not going to change for like next 1 year, right? So this rarely change, and you want to you want CDNs and the browser to cache them for the 1 year, like a very, very long period, right? But if the image is updated, you want to force the revalidation. So for this, there are the number of things that has been introduced, like the ETag or the cache control mechanism. So we will just see how exactly we can do that. So suppose for this we create a get request. Okay, so there is a certain get request of the images that happen, product 123 dot jpeg. This is a certain get request that is being uh, created from the browser to the server. So after that, what would happen is, like the server would say that okay, take this image, but like note one thing, in my cache control there is a max age it will give, and the max age would be like something like a very long thing. So it means that for the next 1 year it is not going to change. And also alongside that, another thing it passes that is being called as ETag. Okay, we will just explain what exactly ETag is. So suppose our ETag is ABC123 over here. So now next time when we are making this request, if the ETag, the client has to send the ETag, and if the ETag matches, that it means that it hasn't been modified. So now it is the responsibility of the client to send the ETag, the same ETag, through this request. And if this particular ETag matches, there is a something called if none match. That means instead of 200 okay, what generally the server send is the HTTP response as 304. That means it is not modified. Okay, so the cached image reused, the ETag avoids the re-downloading of the unchanged file again and again. So this cache control, like how this thing is being achieved, is through cache control max age and also ETag. So this is again one of the great advantage of HTTP 1.1. So alongside those two, there is also a very interesting use case that HTTP 1.1 serves. That is, just to go into that, let's take one example. Suppose you have during downloading any large file, suppose any large movie or even a large data file, you might have seen at times, even if your download gets stuck, browser has the feature to resume the download from the exact point till the point which it got downloaded earlier, and it generally creates a dot data file sort of a thing, and it keep on appending, and when the whole download is completed, you will be able to see your file. So what happens over there is this thing is being served by one of the fundamental of HTTP1, that is being called as range requests. Okay, this range request that what we have mentioned, that is one of the very fundamental thing around the HTTP one which is being used. So let's take one example to understand it a little bit more deeply. So from the user browser, suppose you are requesting a movie like a movie.mp4, and you are doing a HTTP 1.1 call, and your host is some kind of a CDN like a cdn.example.com, and you are reaching out to the movie server. And once you get this request, so this is basically the request that goes. Once you once you do the request, what happens is then you get the response over here. The response come as that this is the total content length of the bytes, 2 GB in bytes. But unfortunately, by the time your download reaches 50%, then suddenly the connection drops. Then what happens? Then the magic starts around the range request. Then what happens is the browser, it detects that the download didn't finish. Okay, browser like detects download did not finish, and after that what it does, it sends a range request. And how does that range request looks? So range request looks something like this. I am just writing it for your understanding. So another request goes like this. I will diagnose the request in a second, give me. Okay, so you see now it is similar to this one, HTTP 1.1, and with the get videos movie mp4, but there is an additional range that is being passed. So what does it tell? This range tells that look, I have already till this byte, so you send me the next byte onward. So probably it has the 50% of it, like till probably this 10737411727, and 28 onwards you please send me. So now what would happen is it is a responsibility of the browser or the client. It sends this request, and from here the server understand that it needs to send the from that given range to the end of the file. And then it checks like various things like whether the file exists, whether the byte range is valid, and whether it supports the partial content or not. And the important thing is this sort of implementation also we can force. For example, if I just look into this code, so over here you can see that it is parsing part by part files. Okay, so it try to understand that what is the range of the file that is available, and over the time it keep on sending it that part which is only required. Okay, so this is a very basic C# implementation. There are like way more other details around it, but just get the idea around very clear that if we have to create this kind of a resume download feature, we have to do it via range request in the HTTP one. With all these details, still there were plenty of issues with the HTTP 1.1. So the first and foremost issues that I want to talk about is with this use case. Suppose uh, you are from your user browser at the same time 6 resources to be get. Suppose you are trying to access something like a www.example.com, and there are 6 resources, like one big image will be there, and alongside that some JS, then some CSS, and then some data. Okay, some different sort of a data, one, data 2, data 3 I have to get. So total 6 resources needs to be get, and for that there definitely will be 6 different get call will be there. So now the problem is, even with keep alive, only one request can be in flight per TCP connection. So what do we mean by in flight? In flight means, so this part in flight means that the request that we are sending, only one can be served at a time. So there is no provision over here with the HTTP 1.1 to serve these things in a parallel way. So what would happen is, suppose an image is being loaded, and suppose this image will be modified to a certain extent using this JS. Okay, so the JS is very important, and there are some other data needs to be annotated over the image, which comes under this data. So what would happen is, even if, because this image is of large size, uh, all these tiny things will have to wait just for the image to be sent or the processed into the request response model. So this is a very, very big problem, and this problem, there is a definitive term to it that is being known as the multiplexing issue. Okay, so what is multiplexing issue? That 100 requests over here, they are being sent over a single connection. Okay, and now this doesn't have that provision. So only solution in the HTTP one is like to there is no way to achieve multiplexing. Only two ways, like open 6 separate connection. So you cannot do a connection reuse, and probably like by this time you understand every TCP connection is a expensive thing. So the moment I open a connection, there is a good amount of OS resources and the network resources are being consumed over there. So more TCP connection means more memory, more kernel overhead, more congestion, and still not enough for the modern pages with 100 plus assets. So like the 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 issue with the multiplexing, if I have to tell, like even parallel calls not enough for modern web pages. Okay, because again, if you see any web page by going into its developer mode, you will see that there are almost 100 plus calls are going on. Okay, so there is no point of uh, doing this 100 plus calls or getting this 100 plus assets just by using HTTP 1.1. And what exactly the resolution of it? To understand it further deeply, let's take a real world example, and let's try to explore what exactly happens into the whole request response model. So suppose we are being now taking a e-commerce site. Like over here you can see this is a shop.example.com, and we are going to get the details of a certain product. Now the important thing is that the moment you move into a product, suppose in the amazon.in, okay, you are trying to load the product, you will see that there is a one large product image is there, and sometimes there are videos as well. There are like the 10 small JS files, like the analytics, cards, recommendations, reviews, whatnot. Okay, and then there are 3 CSS files, like the layout, themes, fonts. There are 3 JSON API calls. So along all with these things, I'm just keeping the number low for our understanding. Suppose there are 19 resources and it goes definitely 100 plus when it goes like if you right now go to amazon.com or amazon.in and just see your developer tools in the network tab, you will see there are probably 100 plus calls are happening at the parallelly. So the very interesting part about HTTP2 is there is only a single connection that is being created, and all the requests that you are seeing like the get product.jpg, get main.css, get card.css, get card.js, all these things that you are seeing, I am only created 3 requests, but like ideally there would be around 19 get requests that there. So all of them are sent, all of them are being sent under this single connection only. Okay, so it is not no separate, it is a very important point here. No separate TCP connection are prepared here. Okay. So under a single connection, this thing goes, and under the same connection only, all the responses keep on coming. So now, if you see in the earlier problem, the problem statement that we had is because this particular product image was large, around 5 MB size, the request 226, like suppose there are total 6 requests are coming up, all because of the one the 226 had to suffer, they had to wait a long time. But here that is not the case. The tiny assets, they will arrive first and there will be no waiting time at all. So this is a very big advantage that you drew on the HTTP2, and that is why if you see any of the current website, if you just go to the network tab and try to find what exactly the protocol that you will it is using, you will always find that is written as a H2. Okay, like the protocol name in your network tab, you will see it as a H2, and if it is HTTP1, you will see it as H1. So right now I'm more than sure like any modern website you open, you will see it H2 or the H3. So this is a very basic um, uh, or like a very fundamental advantage that HTTP2 have over HTTP1. But let's try to understand this is not flawless. Why? Because if you see over there, there we are solving a application layer problem, but still there is a problem of the transport layer HOL blocking still remains, and it crippled the performance on the mobile or the global or any lossy network. So let's understand what exactly the transport layer HOL blocking problem. So HOL blocking is basically the same the multiplexing blocking that we are talking about. So it is being sometimes called the head of the line blocking as well. Head of line blocking as well, but like this is just a term, I would say. Like if you understand what exactly the multiplexing and what are the blockers, you already understand what head of the line is. So let's try to understand what exactly the transport layer HOL blocking is. So suppose you are now using your mobile network, and in mobile network, suppose any of the popular mobile application, like mobile chat application that you are using, and in that there are multiple endpoints are there. For example, suppose there is something like a live chat update. Suppose there is a in your WhatsApp or any other live chat service, you are using this, and also there is one at the same time you try to see someone's profile photo. So what you do is profile photo dot jpg. Okay, this both of these things are some kind of a get requests that are going on. Okay, just for the simplicity I'm putting it like this. So there are two get requests that are going on. So suppose both of them starts at some point of a timestamp of t equal to 0. Now at the t equal to 2 seconds, what happens is at this point of time what would happen is suddenly the connection drops, and that happens very often in the mobile network, right? Like you are traveling in a bus or in a metro and suddenly you hit a tunnel where you do not have any mobile network, and so suddenly the connection drop happens. And the moment the connection drop happens, a very interesting thing happens. Although this whole thing is done under a same, this thing is being done under a same TCP connection. Okay, this is going under a same TCP. So TCP, one of the property is packet order guarantee. So what is the advantage of packet order guarantee? That if there is a certain packet get dropped, for example, during the connection drop, suppose after 2 MB of video, this connection gets dropped, right? So what exactly would happen over here? It would try to see that, or it would try to retransmit the rest of the 2 MB video, although the live chat updates are probably sitting into the TCP buffer of the same mobile network, like or the same mobile phone. So what exactly happens over there is, because this particular profile photo is not fully downloaded, because profile photo dot jpeg not fully downloaded, the TCP buffer next element doesn't get processed. And this is a very big problem, because with the connection drop, now although this might not be like this profile photo might not be a very important thing, right? But that live chat updates are, so it is completely blocking the whole connection. So at times, like when this chats in earlier days, when they used to use HTTP2, often like during the any kind of video upload or any kind of video loading, video download rather, we often used to see that the UI is getting freezed and there is no other chat messages are getting updated. That happened into the earlier version of the WhatsApp, but right now it is totally using the HTTP3 or the other WebSocket features, so it doesn't happen. So let's see this limitation of HTTP2, like this limitation of HTTP2 that we are seeing, it is being known as so this thing is being known as the problem of TCP overhead blocking. Okay, so like if I have to, or transport layer HOL blocking, this particular term that we have written over here, this is very important. This is transport layer head of the line blocking. In the same connection, it gets blocked. So now how it is being resolved? So this is being resolved in HTTP3 using QUIC. So what exactly is QUIC? QUIC is nothing but like a fancy abbreviation of Quick UDP Internet Connections. So you guessed it right. Now instead of TCP, it uses TLS plus QUIC. As you can see over here, this is the TLS plus QUIC, that is the connection it is being used. And what is the key innovation here? So earlier what used to happen is, every TCP connection was a complete stream. Okay, so there is a complete stream of data that was going on. So now this is in H2. So now in H3, what has happened is, the each HTTP stream maps to each HTTP stream maps to separate QUIC stream. So this is basically UDP stream, it gets mapped to. Now the advantage is with this approach that the packet loss in one stream doesn't block other. Okay, so suppose there are, from here my client to my server, from client to my server, some connection streams are being created. Okay, this is one stream under which the, like, the get product.jpg, this is coming. Okay, so although it is a same TCP connection, like the whole things are definitely a same TCP connection, but under this, under that one, excuse me, like it is not same TCP, it is basically the same UDP connection, or rather we can say it is the same connection. Under that there are different streams are being created. Like This is kind of a S1, you can say like stream 1, under which the first one is happening, and then also there is stream 2, and in that way the stream 3 and stream 4, everything goes like that. Okay, so in HTTP 3 the transport layer is no longer TCP, although like I wrote it TCP, that was complete mistake. It is UDP, and via QUIC, that is a quick UDP internet connection. This connection is being created between the client and the server. Okay, and if we just break it down clearly, it is something like that. The application layer is using the HTTP, and the transport layer, instead of instead of TCP, now it start using the QUIC, and the security layer will be using TLS 1.3. So comparison between the HTTP 1 and the HTTP 2 and the HTTP 3 would look something like this. So over here you can see at the application layer we are using HTTP. In the HTTP uh, in the HTTP 1 and HTTP 2 we are using the text based, and whereas for HTTP 3 it is HTTP binary formatting. But the important thing is to understand around the transport layer, this is TCP, and whereas this is the quick UDP internet connection or QUIC. At the security layer is here TLS, and here it is TLS 1.3 built on top of QUIC. So if I have to create a comparison table between HTTP 2 and the HTTP 3, it would somehow look like this. That over here you can see the multiplexing are right now for the HTTP 2 was happening at the application layer. That is why for the each connection there was a single stream, and whereas for here it is happening in the transport in the HTTP 3 over QUIC, the multiplexing is happening in the much deeper layer, that is in the transport layer. So the although the HOL, like the head of the line application layer blocking was done in the HTTP 2, but still the transport layer blocking still existed there, but somehow with the HTTP 3 it got eliminated. So now with this video, I think you probably got the complete idea of how HTTP 1, 2 and 3 whole transition happened over the time in the internet, and how the web evaluation web kind of got the total evolution over the time. And there are of course way other deep things around it, but like we are not taking into the scope, because in that case the video will be really long. So in case you have any doubt, please post it in the comments. I will try my level best to answer your queries. See you in my next video. Till then, stay awesome. Bye.